Winter 17, Test 4, Part 4, question number 5. We have an alkyl bromide, a strong nucleophile that could be a strong base. So you're thinking about substitution or elimination, and a polar aprotic solvent. Clearly we're doing the substitution, not the elimination. Strong nucleophile favors the SN2, especially since there's a polar aprotic solvent. Looking at the fact there's 1 point in this question as well is a big hint. SN2. Your titles would be, you were told that chromic acid oxidation will be on your final and you will have no way of avoiding it because there will be 2 consecutive chromic acid oxidations. You need to protonate the double bond to O first to generate an oxonium, which makes the chromium more reactive towards a nucleophile. That's the reason you're doing this. I'm going to save a little time by circling this group here, calling it R. Show your protonated chromic acid. Do not forget your formal charge on the oxygen that has 3 bonds. This has activated the chromium towards attack by even a poor nucleophile, such as an alcohol. We neutralize the oxonium by breaking the pi and putting a lone pair on the O, and that generates this intermediate here. That generates this species here. It's at this time that I realized that this hydrogen sulfate I made in step 1 is now needed because it's going to neutralize my new oxonium ion and generate this species over here. What we have here is a chromate ester that has an extra H here and an extra OH here. It is called a chromate ester hydrate. How do you get rid of a hydrate and make it into a chromate ester? It's called dehydration. The arrows in dehydration are almost identical to the arrows in tautomerization. You need an acid-base conjugate pair for either acid-catalyzed dehydration or tautomerization. Our base that's available here is the hydrogen sulfate base. Our acid is its conjugate acid, sulfuric acid. Base does what bases do, grabs a proton. We resonate in to make a pi. And this leaves as it's protonating. If it does not protonate, it's not a good leaving group. And you see how sulfuric acid is used here and made here, thus rendering it into a state of catalysis. We used sulfuric acid as a catalyst twice in this mechanism. Here we used it and here we made it. That's the first time we used it as a catalyst. And the second time was in the dehydration step, which we just accomplished here. The key to the oxidation step is figuring out what H ends up on the water to become hydronium, and it's always the H on the carbon attached to the oxygen that needs to become a carbonyl. So we're going to draw that H. Going to put a lone pair on our water. It's going to grab the hydrogen. This becomes a pi, and this leaves with an extra pair of electrons on chromium, thus reducing the chromium. And that step is the oxidation step for the carbon. Carbon had 1 bond to O, now it has another bond to the more electronegative O. It got oxidized, the inorganic molecule got reduced. And that's the end of that. There was a reaction that leads to this molecule in sequence D, but it's not one that you're going to see on your final. It's the reaction of a nucleophile with a ketone again. But this one does show up on the final, the addition of an alcohol to an alkene in the same molecule. And it's the same as acid catalyzed hydration, except you're using ROH instead of HOH. So step 1 is not to protonate the OH. You need to keep the O. You're not making the O leave. It's right there. We're protonating our alkene to generate a cation down here or up here, and I think the answer to the question, why is it up here, is the fact that there's a new bond to that carbon there. The better answer is, if there's a cation there, it's called benzylic. One away from a benzene. That's a much better cation than a secondary. Secondary benzylic cation is better than a secondary. So let's generate a secondary benzylic cation. So we've got a benzene on top. We've got a cyclohexene. Oh, that's terrible. We're going to generate a cation here. And it's special because it's benzylic. Secondary, yes, but benzylic. That's the equivalent of being 3.5 degrees of cation stability, isn't it? Secondary benzylic is roughly the same as saying 3.5 degree cation. All right. Now I need to make the bond from the O to the cation. Use a lone pair. Make the bond from the O to the cation. Generate one more intermediate, and we're almost there. So you've made this oxonium species here, which is the conjugate acid of the final product. To neutralize it, you're going to need to use your hydrogen sulfate, which you generated in step number 1. And it grabs the H, neutralizes the O, and you've made your ether. Alcohols add to alkenes in the presence of an acid catalyst. That'd be the title. Acid catalyzed addition of ROH to alkene would be your title for the final. And there you have it.